Hello, everybody. So today we're going to be taking a look at another theorem. We just looked at the extreme value theorem, guaranteeing maxes and mins, as long as the function was continuous on a closed interval. Now we're going to take a look at the mean value theorem. And there is a mean value theorem for derivatives and one for integrals or antiderivatives, which we'll get to later. But this is one big, huge, important formula that's going to be on the AP exam. So have your foldable ready. We're going to stick something on there. And we're going to practice a couple problems here. So as always, take notes in your notebook, pause me when you need to, try to practice, maybe try a problem on your own, and rewind when something doesn't make sense. All right, here we go. So my first question is set up like this. Car is stopped at a stoplight and it accelerates from 0 and takes 8 seconds to go 352 feet. Find its average velocity during that 8-second interval in, let's say, we'll just, yes, find that average velocity during the 8-second interval in miles per hour. All right, so first of all, our average velocity, this is something that we were talking about before. So it's my position at time 8 minus my position at time 0 all over 8 minus 0. Well, position at 8 minus the position at 0, that's just my displacement. So that's 352 feet in a matter of 8 seconds. And 352 divided by 8, I get 44 feet per second. So that's my average velocity, but that's not in miles per hour. That's why I paused earlier, just to remember what we're doing here. So I'm going to do a little conversion. So I'm going to change feet to miles. There's 5,280 feet in a mile. And I now want to go seconds to hours. And there's 3,600 seconds in 1 hour. And just keep in mind why I put those where I did. Feet and feet cancel, and seconds cancel. And so on my calculator, 44 times 3,600 divided by 5,280 gives me, switch pen colors, 30 miles per hour. So during that little 8-second interval, I had an average velocity of 30 miles per hour. So the question is, did I go 30 miles per hour at some point? And if you think about it, if 30 miles per hour is my average and I'm accelerating, at some point I'm at 0, and at some point I'm going to have to be greater than 30 miles per hour for my average to be 30. So wouldn't it come to make sense that somewhere during that interval I had to at least be going 30 miles per hour? So yeah, and that's what the mean value theorem, mean meaning average. So at some point, if my average velocity, will it be equal to my instantaneous velocity? And it will, as long as certain conditions are met. Well, let's back up to what was discovered first by Michel Rolle back in the 1600s, is that his theorem says, okay, so let's say I've got a function and on a closed interval, and the value of the function at a and b are exactly the same. So it's whatever these two values here in my picture are. Well, what he was saying is that as long as I've got a polynomial function, and the thing about polynomial functions is that they are continuous and differentiable. They don't have denominators, so you don't get any kinds of discontinuities, and they are very differentiable, just cubics, quartics, quadratics, things like that. So I know I'm going to have a nice smooth curve in between. And he's saying, well, if those two values are the same, and we know then the slope between those 2 points is going to be 0, because there's the same y value, then he's saying there's got to be some point in the graph where the slope is also equal to 0. And that point we're going to call value c. So if he said if I have a polynomial function and the two values were equal, then there's some point c where the slope is going to be equal to 0. Well, that's great as long as those 2 points are the same. That doesn't always happen. So through history, Rolle's theorem was to talk about any points, and they could be anywhere. So the mean value theorem, again, mean meaning average, says that if I have a function that's continuous on a closed interval and differentiable over the open interval, then somewhere between A and B, there's going to be a point where the slope of the tangent line is equal to the slope of the secant line, the average rate of change. So what we're really saying is that my instantaneous rate of change will be equal to my average rate of change somewhere at some value of C. And it could be multiple values of C, but at least we're guaranteed that there's one point, as long as the two conditions are met, continuous and differentiable. So again, this is my slope of my tangent, and we're saying that at some point, if those two conditions are true, then the slope of the tangent will be equal to the slope of the secant at some point. So yes, this needs to go in a foldable. On the outside of the foldable, mean value theorem for derivatives. Inside the foldable, I want all of this. Continuous over a closed interval, differentiable on an open interval. Then the formula is this formula, which is what you're going to wind up remembering. But I would also squeeze in there IROC equals AROC, or slope of tangent equals the slope of the secant. So pause me now so you can get that into your foldable. So here's what that physically looks like. So I've got some interval from A to B, closed interval. I've got a function that's continuous, no jumps, holes, or asymptotes. And again, this doesn't have to be polynomial functions, can be any kind of a function. Smooth and continuous. So it's continuous and differentiable within that interval. Then there's going to be some point C where the slope of the tangent is equal to the slope of the secant. Basically, the tangent and the secant lines would be parallel during that. And that's just what we're talking about with my speed problem. I can figure out an overall average rate of change if this was a position time function, and then I'd know the instantaneous rate of change. And not only that, I would be able to say, okay, yeah, I am going to go 30 miles per hour at some point during it. And not only that, I'll be able to figure out when. When was I going 30 miles per hour, which was my overall average rate of change, or my overall speed. So let's take a look. This is a good kind of picture to maybe stick in your notes. Again, slope of the secant line and then slope of the tangent line. And I would probably say secant instead of the chord. Okay, so let's see what the typical question is. So given this polynomial function, this quadratic, on the closed interval from 3 to 8, I would like to find the value of C that satisfies the mean value theorem. Well, first of all, there's going to be some questions, and I'm going to tell you right now, in the AP exam, they are looking to see that you know these two conditions. If these two conditions aren't met, it's not continuous and it's not differentiable in these intervals, then the mean value theorem doesn't guarantee that the slope of the tangent will equal the slope of the secant somewhere within that interval. Could it happen? Sure. Is it guaranteed to happen? No. So in this case, mean value theorem does apply because I've got a nice simple polynomial function, and within this interval it is continuous and differentiable because I know that parabolas are. So I want to find the value of C that satisfies the mean value theorem. So what is my instantaneous rate of change? What is f prime of C? Well, f prime of C is going to be 2c plus 4. This is just the derivative of the function, but with a c in it. And now equaling f of b minus f of a all over b minus a. Well, that's going to be f of 8 minus f of 3 all over 8 minus 3. So I got 2c plus 4, and I've got this all set up my calculator. So f of 8 into this equation, I'm getting 99. And at 3, I'm getting 24. So 2c plus 4, that is the derivative, the slope of the tangent line anywhere. And here I've got 75 divided by 5. So 2c plus 4 equals 15. And doesn't take too much work here. So at 5.5, that is the place on the parabola where the slope of the tangent line will be equal to the slope of the secant line. And what is that slope? Well, we just found it. It was 15. So you can see what I'm doing here. All this work over here on the right, all of this was in an effort to figure out what is the slope of the secant. What is the average rate of change? This is my A rock. Well, over here on the left, this is my instantaneous rate of change at any point, and I want to find where is the point where it would have an average rate of change of 15. It's a pretty common question on the exam, and it's going to be coming in a bunch of different forms that we'll see. So some questions are going to ask to say, is the mean value theorem guaranteed here? And in this case it is, but we will be seeing some places where they are not continuous or not differentiable on the interval. Another thing that we're going to start looking into, and is what I had said before, is that the whole task ahead of us is to use calculus to describe the behavior of graphs and functions. So mathematicians didn't have graphing calculators hundreds of years ago, so they had to use the calculus to actually figure out what these graphs look like and what their behaviors are doing. And that's what we're going to embark on over the next. We've already started looking for when slopes are 0, and now we're finding where slopes, where the average rate of change equals the instantaneous rate of change. But something to keep in mind, and we're going to start a lab here soon that deals with this, is that a function is increasing over an interval if I have a positive derivative. Remember what derivatives are? Derivatives represent slopes. So if I have a positive slope, that must mean the function's increasing. If I have a negative slope or a negative derivative, the function must be decreasing. So let's kind of use that to answer a question like this. Use calculus to determine the local extremum and the intervals where the function is increasing and decreasing. And I'm giving you a sneak peek of what we're heading into in our lab that's coming up. Okay, so how do I find local extrema? I find local critical points, which is where the derivative is 0 or undefined. So super easy derivative here. And I'm going to set it equal to 0. Can't set it equal to undefined. There's no fraction. So can't set a denominator equal to 0. And I get x is equal to -1/2. And what have we done? Well, we've tested some points on either side to see where the function is. And we looked at some of those function values. Well, I'm going to switch it up here. And I'm going to use a little sign chart. And this is going to be a first derivative sign chart. So I'm going to call it y prime. Now, I was doing this the other day when we were dealing with velocities and accelerations, which are also derivatives, but now I'm just doing it in general. I have a first derivative sign chart, and I'm going to put on my critical point -1/2, and I'm saying that the first derivative is 0 there. Well, now instead of testing values of the function left and right, I'm going to test derivatives to the left and the right. So let me pick a point like 0. That's to the right of -1/2. What is the derivative at 0? Well, it's 1, so therefore it's positive. And it's going to be positive all the way to infinity. Well, how do I know no other changes are going to happen after that? Well, because I've found all the critical points. There's no other critical points from -1/2 to infinity, so it's all going to be this monotonic behavior of increasing. And that's my second giveaway, is that what does that tell me about the original function? I'm going to put that underneath my sign chart, and that tells me my original function is increasing because I had positive first derivative values. All right, so let's test to the left. Easy number to the left of -1/2, like -1. Put -1 into the derivative. What do we get? I get -1, so that means all of these values are negative. And what does that imply that the original function was doing? Well, it was decreasing. Well, I think I answered my intervals where I'm increasing and decreasing. I'm going to be increasing from -1/2 to infinity. And I'm going to be decreasing from -infinity to -1/2. The only thing I didn't answer is where my local extrema are. Well, I know now, based upon this sign chart, if I've got a function that's decreasing followed by increasing with a slope of 0 in between, I mean, can we picture what that looks like? Decreasing with a slope of 0 and increasing? Hey, guess what? You just drew a parabola. Yeah. We knew it was a parabola, but now I've justified it here, so I know now, because of the behavior from decreasing to increasing, I know I'm going to have at least a local min. Now, why do I say at least? Well, because In another situation, there might be other critical points, and I might need to test or even possibly endpoints to see what's going on. Yes, in this case, it is also an absolute min. So we're going to venture into a new study here of using these sign charts to tell the behavior of the function, whether or not it's increasing or decreasing based upon the first derivative. And we're going to also do this in terms of the second derivative. And if you remember, we hadn't talked about it a lot, but the second derivative, what does that tell me about the original function? The second derivative tells me about the concavity of the original function. So we're going to talk about that up here soon. All right, I'm going to stop here. We still have another thing to talk about, but we will talk about it in a different situation. We'll talk about it soon, about antiderivatives, which you have been playing around with a little bit here. So at this point, need you to check online to see what assignment that we have coming up.